Now, if you haven't seen my other videos on the habitability zone, I'm just going to kind of recap that and how that alters with regards to star type, and then we'll go on to the actual spin speed of a planet. So the habitable zone, which is this green zone around the star where the planet is orbiting, which is the blue kind of line, this is the distance from a star where you'd get liquid water on the planet. It's a fairly broad term because it depends on quite a lot of things, but it's this area that a planet can basically reside in and have liquid water on its surface, and it would then be classed as habitable. Again, there's a few more things to that, parameters that can alter it, but generally we can calculate where that is, and I've done a separate video on that anyway. So if it's too close in the red zone there, the planet will be too hot. If it's in the blue zone, then it's going to be too cold. So it kind of needs to sit in this like Goldilocks zone, just about right. That's kind of where Earth is. But we can get a little bit closer and a bit further away if we have slightly different compositions and atmosphere and things like that, or rotations at least as well. But anyway, we've got this green zone, which is just about right. Not too hot, not too cold. And it does change with star type. So stars are not one size, one brightness, one mass. They do change. So here you've got an example of the sun and a red dwarf at the bottom with their planets orbiting. And the light kind of blue band there is the habitable zone. And you can see with the red dwarf, it's actually closer. And that's because it doesn't kick out as much energy. So the planets have to be closer in order to be habitable. So red dwarf stars, as I mentioned, you've got to get much closer for them to be habitable. They just don't kick out as much energy as the sun or even bigger stars. That can be a bit of a problem with regards to habitability because they do kick out some flares. Again, I've done a separate video on that. If you've got a more massive star, they'll be hotter, they're also bigger, there's a lot more energy being emitted from them, they're more luminous, and your planets need to be much further away from the star. Now, really massive stars actually have a lack of planets orbiting them anyway, but you need to be further away if you want them to be habitable at least. Now, the rotation period is important as well, and the rotation period to orbital period is also kind of important. So this is how fast the planet rotates with regards to its orbital period. Why is that important? Well, we do have something that's known as tidal locking, and the moon is tidally locked. It's always got the same face facing towards us, and you know, if you were standing on the surface, you'd always see the sun. From the moon, you'd always see the Earth, and that means that you're also going to get illuminated, or your days and nights don't change, not like we do here. So that rotation period of the planet, which gives us our day and night, is important with regards to how long it takes to go around the star. Now, if it's too slow, as I mentioned, then one side is going to get a lot more energy from that star than the other side, so it'll end up being very hot. And then the other side won't get much energy at all, and that will be much cooler. Now, this is it's not taking into consideration the atmosphere. So let's say we've got a rocky planet, maybe like Mars or Mercury, then that just heats up that surface that's facing towards us if it's going too slow. And you get a difference in temperature between the two sides that's much greater than we would have on Earth at the moment. Now, tidal locking is where it rotates once for every time it goes around the star or the planet, depending on what it is. This is known as tidal locking. So you've always got that same face facing towards it. That means that you're only going to get the starlight hitting one side of the planet. What does that do? Well, your day side is going to be too hot and your night side is going to be very cold. So you've got a huge difference in temperature there of where that starlight is making it to the actual planet. Now, again, I did a separate video on this, but you can have habitability on these tidally locked planets because the terminator, which is kind of just in the middle, so if you were to stand at the terminator, it'd kind of be like a perpetual twilight or sunset, sunrise. So sun or the star would be very low down on the horizon, and that can be just about the right temperature. It gets just about the right energy from its star. But the other two sides, they have huge temperature differences. If you've got a much faster rotation, then you're more likely to get a more even distribution of the energy that's falling on the surface. So more likely you're going to get more even distribution there. Again, at this current moment, we're not really considering the atmosphere, we're just considering maybe like a rocky planet with minimal atmosphere. So more even surface distribution of that energy and temperature. However, if we do have an atmosphere and we've got extremes in temperature, so like that tidally locked planet's rotating too slow, you're going to get quite a significant amount of energy transport. What does that mean? Well, on the hot side, that air gets heated, the atmosphere gets heated, it's going to rise up and it will circulate round to the cold side. That's actually kind of a good thing because it will send heat from the hot side to the cool side, which then gives you a more even distribution of temperature over the actual planet itself. So we get this circulation of energy if it's slow anyway. So here you've got the hot air rising, it then moves to the cold side. The downside of that is if you do have quite significant circulation, you're going to have quite high winds. That can obviously drive storms, things like that. So not necessarily great for habitability. And again, it depends on the specifics of it. But if you've got significant amount of circulation in the atmosphere, that's going to drive, quite significant winds. So what is the ideal spin speed? Well, again, it depends on the atmosphere, how much circulation is occurring, but you can actually have a slow rotator which can be cooler compared to a fast rotator like Earth. Well, Earth's not necessarily a fast rotator. Earth's kind of around about right for its atmosphere, but we could have a slow rotating planet. It's a bit like Venus, and it could have a slightly different atmosphere, and it could be habitable closer to the actual star than Earth is currently. So it does depend on the atmosphere, but you can actually get slower rotators if you've got a good amount of circulation cooling it down. Now also, if the Coriolis force gets too large, which basically means it's rotating too fast, then it alters the structure of the atmospheric circulation as well. So not only are we getting some circulation there and energy transport, it can alter how that's done in different locations. Like it could happen maybe more at the equator or the poles or something. So that also has an impact. And when that rotation gets too high, it changes the structure of that. So just to kind of finish really, I suppose Earth is kind of about right. You're looking, around a day plus or minus quite a few hours, really, depending on a few parameters. So you don't want it too slow, you don't want it too fast either. But if it is slow, then it depends on the atmosphere and you can get a cooling effect anyway. So thank you for watching, and if you enjoy the videos, then consider becoming a member of the channel. It helps us obviously support the channel, and so thank you for watching.